Okay, great. Um, so I'm Matt. I think I've met a number of people who have joined in. And this was a talk that I've been kind of thinking about giving for a while because memory safe languages have been coming up more and more often on our radar as developers for various reasons. And one thing I noticed in talking to people around the lab was there's some need to not like advocate for these languages, but get people to think about why we should care about them and how we should think about them in terms of our own work. And so this talk is kind of intended to be aiming at that. So, and to be honest, if you looked at the slide, the file name of this talk, it's Memory Safe Languages Talk Take 4. This was a surprisingly difficult talk to write because I had to kind of resist the urge to fall into language advocacy, since that's not my goal here. So the overview of the talk. So I'm going to talk a little bit about like why are we even talking about memory safe languages and why have they come onto the radar a bit more strongly in the last few years. And then talk a bit about some examples out there and some success stories. But also I wanted to share some skepticism that you hear about the languages that come from developers here and out in the community. And then the last part of the talk is kind of context of how should we think of these at the lab and kind of what are my thoughts about how they should be applied to our work. And I've intentionally left this talk to not take the full hour slot because I wanted to give time for questions. I'm sure people will have opinions. And so I'm kind of curious to hear about that. I do have trouble seeing the chat during this. So if I don't see a question, it's not because I'm ignoring you. It's because I didn't see the little bubble on my screen. So before I go, I realized that not everybody is familiar with why we care about memory safe languages. So what are the kind of memory safety issues that arise when we're writing code? And so basically memory safety is one of the biggest sources of bugs in software. I think a lot of us realize that. And the kinds of bugs that show up usually are in the form of unexpected code execution. It turns out if you can kind of wander around memory, you can make code that you didn't expect run. You can have data loss, where that data loss either means the data disappears or data is lost to other people that you didn't want to be lost to, or data may be corrupted. And sometimes it manifests in system instability. So the famous Windows blue screen of death that people were familiar with for a while, that was often memory safety issues that were causing the problems. And so the kind of examples of issues that show up in code that fall under this category would be things like out of bounds memory accesses. So accessing a piece of memory that you really aren't supposed to, dereferencing null pointers, data races. So unpredictable orderings of reads and writes are a class of memory safety problem. Using uninitialized variables or having uninitialized variables, leaking memory, use after free errors, and so on. So basically any time that you're just using memory in a way that's not considered correct by some definition of correct. So if I had to sum up, like, why is this coming up? Kind of the one-line summary of why we seem to be talking about these days is that memory safe languages represent this technological and mindset shift from an opt-in model of safety for software to an opt-out model of safety for software. That, I think, is kind of it. Like, that's really what these languages are all about, is this shift from opt-in safety to opt-out safety. So there's a little bit to unpack there. Like, what does this actually mean? So the opt-in model of safety, this is what we're used to if we're using C and C++, where the language definition, the standard that just defines the language itself, doesn't really provide safety guarantees out of the box. So undefined behaviors are part of the language. You can do things like pointer arithmetic, which means you can take a pointer and then you can just start changing it. And next thing you know, you're referring to an address you shouldn't have. You don't have bounce checking typically. And memory management is done manually. Now, with the opt-in model, the reason it's called opt-in is that you can opt into safety through various mechanisms. So very commonly, you'll see people saying, well, you got to be disciplined, you have to adopt best practices. And sometimes you'll also see careful design of a project that tries to take into account safety. LLVM is a good example of this. Most recently, I was looking through the internals of the Flang front end with one of my colleagues. And if you look carefully in there, you'll see this thing called an indirection object, which is basically a way of wrapping a pointer up and also giving it some checks to make sure that, for example, that pointer is never null. And so that allows them to enforce this safety constraint that there should never be a null pointer when an indirection object is being used. You can also use safe components that the language provides as part of libraries. So either STD and C++ often has various fancy pointers and other things that are helpful. And sometimes you can also use third-party libraries. But because these are not part of the language standard, like boost things are not, oftentimes you have to then appeal to things like static analysis tools or runtime assertions to check to make sure you're using things correctly, because the compiler often can't exclude unsafe code, because if it's legal code, the compiler is obligated to compile it. So this is where it's kind of the opt-in model. You have to choose to be safe, and then you have to keep yourself disciplined when you're applying the safety. And basically, this is what we've done for forever. My whole time in computing, using C and C++, even when I first learned it in the 90s, this was, we knew about these problems and we knew the mechanisms to do it, and so you could opt into safety. The thing is it's not really going very well because we're still seeing the same bugs popping up over and over and over. And the people who build these languages kind of keep telling us, well, trust us, this time we're going to get it right. Which sometimes feels like somebody at a slot machine who's like, I know it's going to hit now, just give it time. And so this is the opt-in model that we currently live in. The opt-out model, though, is basically saying, well, what if we just kind of flip things around and we make it so that the default behavior of the language is not unsafe? So pointers by default are more limited. You don't have null pointers sometimes. So Tony Hoare is quoted as saying, like, the introduction of the null reference in algol W was his billion-dollar mistake because it's caused such a gigantic mess. And that was 1965. Ironically, if you look at his full quote when he talks about that, when he introduced that to algol W, he was actually also researching how to do safe memory access and safe memory management. So even in the 60s, they knew safety was possible. So you also have undefined behaviors, severely limited or eliminated entirely. Bounds checking is on by default, and you have some form of automatic memory management, either automatic reference counting, that's what ARC is, garbage collection, GC, or a static model of borrowing and lifetimes, which is kind of the Rust model of things. And then when you know that you need to do something where the safeties are getting in your way, you can opt out of them. And so you can still do what you want to do if you really want to be unsafe, but you do so in a controlled and isolated way. So you either have unsafe code regions, you use a foreign function interface, or something that allows you to kind of escape the safety, do the dangerous thing, but do so in a controlled way. And the benefit of these is that it reduces the chance of human error. You're not relying on discipline, and you're really trying to get the compiler to statically check as much as possible with respect to memory safety. And the whole concept is basically that mistakes are avoidable if you just can't write them down in the first place. And so if you're working in this core language and you're not in the unsafe parts, you're getting a lot of guarantees, and the compiler is able to prevent you from just writing down bad code. So why is it that, like I said, when I first learned C and C++, we knew about some of these things, but we didn't really hear about memory safe languages all that much. It's only in the last few years that they've really ramped up. And I'd argue that we've had a long time to get the opt-in model of safety right, and it's arguably not going very well. But the computing community seems to have come to this realization that there's costs associated with everything, and that it seems like the cost of adding memory safety to existing languages, building the tools to help us find the safety bugs, fixing the safety bugs, is beginning to outweigh the costs of adopting new languages, integrating them into the existing code bases, and doing workforce development so that people can learn and become proficient in these languages. And what's even worse, and I think this is the factor that's going to be driving, has been driving industry's interest in these languages, is that I think people, especially lawyers, are anticipating that there's some additional costs coming. So I think people are seeing that there may become legal liability for software defects. It's amazing right now that companies can have defects that cause massive loss of information and money. And their kind of response is like, oops, there's a new update, just download it. So I think people have realized that there may become maybe consequences that are quite costly. And it's likely to see stronger regulatory requirements around software. We're not seeing them right now, but I'm guessing that you're going to start to see that. And as soon as you have that, that's going to get more expensive as well. And so in anticipation of these kind of growing costs of kind of the way things currently are, these other languages are giving us an option to possibly avoid those costs. Thinking long term, the immediate cost may be much more to adopt one of these new languages, but over the long run, it's looking like they'll be cheaper. So talking a little bit about the skepticism people have about these languages. So there's really no universal agreement about which route is best. I think you will definitely be able to find people on the internet or in person who have strong opinions about one or the other. But there's the jury's kind of out. The sort of safer opt-in model of kind of using better C++ features or better C features. Some people argue for that. Some people argue this opt-out model is better. It's also very easy to still write bugs in memory safe languages. So sometimes people tout them as being like, oh, if you use Rust or Swift or something, you'll suddenly have code that doesn't have bugs. It's like, no, you'll still have bugs. They'll just be memory safe bugs. I've joked with people that this won't make malware go away. It just means that the malware authors will be writing higher quality malware. So it just means that the bugs that are kind of dominating our security and safety landscape will stop being memory safe bugs. And it turns out there's actually quite a few of them. So there are very real concerns about memory safe languages and the learning, things like the learning curve, the stability of the languages, supply chain considerations, and the fact that they're not useful in certain domains yet. And just to kind of see some real complaints that people have had, the Linux kernel mailing list is a good example of this. So they've adopted Rust, and you're seeing kind of a lot of skepticism from developers there, where they're seeing that like the syntax of these languages can be painful to learn if you're coming from an existing language like C or C++. The difference in the language model itself can make the software design feel very awkward. And so people find it harder sometimes to integrate with existing languages. There's also the skills gap. The workforce they're not familiar with them. And some of the tools are immature. They're not available on all platforms, and they're not as solid as people would like them to be. But the last comment I put on here is an interesting one, where I noticed that somebody said, there was a thread where somebody was suggesting they should move to C++. And somebody said that if you want C++ to achieve what Rust can already do, you need the compiler to help you. It needs to stop the stupid before you can even write it. Otherwise, you're still relying on human factors. And the C++ compilers won't stop you from writing the stupid stuff. So it's an interesting thing to watch this discussion go on about the pros and cons of both models. So if I was to go through kind of what are the examples of these languages in the wild, so Rust is the most common one that you've probably heard about. And the reason for that is it's the first mainstream, it's the first memory safe language to have fit systems developer needs. So this is like operating systems developers. And the big thing that it did that other ones haven't done is it had a static memory model. So you achieve safety in memory by this, what they call a lifetime and borrowing model. So you're very explicit about how long memory that you've allocated lives. And when you're passing it around in the program, you're very explicit about which component of the program owns the memory at any given point in time. And this is statically enforced by the compiler. So you don't have a garbage collector, you don't have automatic reference counting. And so you can really do some fine-grained performance tuning. The ownership model is very good for reasoning about data races, which comes up a lot in system software. You can have unsafe code that you can integrate with safe code, and it's competitive with C and C++. And this is the language that's had the most kind of uptake, where you probably are running Rust code right now and don't even realize it. So the Windows kernel has integrated Rust code in some components. Android uses Rust code. The Linux kernel has adopted Rust code, although they're skeptical. And a ton of web and internet infrastructure uses it. So Rust is the one most people think of with memory safe languages, but there are others. Go is another one, and interestingly, Go is a descendant of C. It's descended from C via Aleph and Limbo, which are the languages for Plan 9 and Inferno. But it has a heavy emphasis on concurrency, which comes up a lot in systems applications and networked applications. Its memory management is by a garbage collection. It has bounds checking, and it's designed for simplicity, which made some people grumpy because they excluded some features of the language that people thought should be there. But it turns out it's had quite a bit of uptake in the server and the infrastructure world, even without some of the fancy features. And so this runs a lot of the internet infrastructure that we use on a daily basis, has Go sitting underneath it, helping keep things running. Outside the systems world, one that doesn't get as much love as I think it should is Swift. This is Apple's language that Chris Latner, one of the LLVM developers, was one of the inventors of. And this is an interesting one because Apple's realized that they're constantly fighting memory safety problems throughout their entire software stack. And this is why we keep getting iOS updates and other things. And they're trying to replace every language in their stack: C, C++, Objective-C, and Objective-C++. They want to replace with Swift. It's an automatically reference counted language, so it doesn't have a garbage collector. It's ARC. But what's interesting about it is they designed it so that interoperability with existing languages was very simple. And the rationale there is that they can't replace everything all at once. And so as they're incrementally replacing things, it needs to interoperate with all the existing C, C++, Objective-C, and Objective-C++ code. But also it has to work with all the code people outside of Apple wrote. So everybody who's written libraries, applications, they're not going to all move to Swift right away. And so even if Apple replaces their whole stack, it has to play nicely with all those external things. And the external code has to be able to work without knowing that Apple's swapped out C for Swift. It's also designed to be easy to learn. So it's had strong uptake, obviously, in Apple's ecosystem, a little bit less strong outside of it. And I'd argue that the main reason for that is a perception problem. Some people perceive it as just being like for Apple platforms, but it is available on all major operating systems. And there's an open source compiler for it. The last one that's kind of first class slide here is Java and C#. I lump those two together, even though, yes, they're different languages, but they represent these bytecode based languages. And those are important because they abstract the machine away completely. You target a virtual machine, and then you rely on just-in-time compilation to actually build the code and compile it for your actual machine. They're garbage collection based. They don't allow any pointer arithmetic. But what's two things that I think are quite interesting about them is, first, they have more than just safety features for memory. They also have what's called an effects system in their type system. And this allows you to look at a piece of code and not only know what its API is, but what effects it may have with respect to errors. And this allows you to check to make sure that errors are not being ignored. The other interesting feature of these languages is that most of the safety is a side effect of the virtual machine and the just-in-time compiler. So a lot of other languages are built on top of this that
Matt, we can't hear you anymore.
Wondering if his that box on the side, that fail-safe box, I don't know if he's using one, but it usually has a 30-minute timeout.
Okay. Yeah, Matt, if you can still hear us, we can't hear you anymore. Okay, yeah, sorry about that, everyone. So let's see if we can get this figured out.
Well, the slides aren't advancing either, so it might have been a network drop.
Yeah, seems like it.
He said he has network problems and he's reconnecting.
Okay, let's just give him a few minutes then.
I guess I don't know how far I got through this one, but the big thing with this one is that the Java or the bytecode-based languages, they provide safety through this virtual machine, and they do have quite a heavy presence out in the industry world. But beyond these examples in the wild, I kind of listed a handful of honorable mentions that don't really deserve slides on their own. But Python is arguably a memory-safe language. It does provide a lot of features to protect you from the underlying machine. You can integrate code that's not in Python quite easily. But its dynamic features can lead to other non-memory safety related issues that make it a kind of sort of safe language. There's also the functional languages. They tend to be in the memory safe world because they also tend to have very strong type systems that allow you to prevent a whole bunch of bugs. And they do have industrial uptake, especially in the high assurance world, the compilers world. But they tend to be too far outside the comfort zone of most developers to really kind of take root. And then Ada is worth mentioning because it was designed with safety in mind, and it's quite a nice language if you're writing critical systems, but it's possible within the language to work around the safety features and easily write unsafe code. But I think it's interesting because it's the only language that I've encountered that allows you to have this concept of a profile, where you can define a subset of the language and then have the compiler enforce that. If we had that for C++, I think it would kind of change the game for C++, where you could start excluding things that are unsafe and let the compiler kind of enforce that exclusion. And there's ton of other languages that I missed. So just a success story that I thought was interesting, and Google was kind enough to have a nice blog post about this about a year ago. But they've observed this kind of nice drop in memory safety vulnerabilities with Android. And they're quite proud of this. But around the same time that they made this change, the big thing they wanted to point out is that Android 13, when they noticed this big change, that was the first time that they released a version of the operating system where the most of the code was in a memory safe language. Basically, Rust, Java, and Kotlin were the major languages that kind of began to take the place of the unsafe languages like C and C++. And this was also the first year that they didn't see memory safety vulnerabilities being the majority of its vulnerabilities. Interesting that they say it's not the majority of vulnerabilities. Now they have lots of other vulnerabilities. They're just coming from something other than memory safety. And so this is a good thing. So some of the myths that are out there about these languages is that some people perceive them as being like academic toys, and that all the noise we're hearing is more or less just the usual academics trying to get people excited so they can get their grants funded. The thing is industry is leading the charge on these. So all the major languages that I listed have come from something other than universities. So Swift came from Apple, C# from Microsoft, Java's Oracle and Sun, Rust was Mozilla's language, Go is Google's, and so on. The languages you hear about in the programming languages conferences, you're not hearing about those in the memory safe language discussion. Those weird languages are staying off in their strange corners of the programming languages conferences. Another thing is that memory safe languages are sometimes regarded as a fad, and that if we just kind of carry on with our existing tools, we'll let this fad die off and the languages will go away and we can carry on. The only indicator I have, and now obviously it's stupid to try and predict that a fad is going to die or stick. Like, I don't know the future, but the indicator I have that it probably is going to stick around is that industry hates spending money. I know this because between my time at LLNL and Livermore, I was in industry and I noticed they really, really hate spending money. And they are spending a ton of money on memory safe language migration. And so the fact that they're making that choice to spend tons of money on this kind of tells me that they've decided that it's not going to be a transient thing. And to be honest, I think the fact that they're investing so much in it is going to take something that could have been a fad and may make it actually stick around, since now they have poured so much investment into it. And the last one is, some people say memory safe languages are inherently inefficient and we need absolute performance. And I'd argue this is a fair critique if you're looking at when the languages were introduced. So they were introduced, often the techniques that are in these languages came about decades ago. And their performance was not great. The garbage collector got in the way all the time, and some of the static checking or some of the runtime guarantees got in the way all the time. But compilers and runtime systems now are significantly better than they were 40 years ago. And so I'd argue that the inherent inefficiency is not so much of a concern these days. And even more, because I said these are opt-out languages, for critical performance, they give you escape hatches. And so you can go off and write things in memory safe languages, and then when you need to, you can opt out to get performance. And so that's kind of a myth that you're going to be sacrificing performance if you start to adopt these. And the last one, it's not really a myth, but it's a complaint that I've observed when working with people with these, is people get frustrated because they say, oh, I'm fighting the compiler all the time. I don't have to fight the compiler as much with my existing language. I just want to run my code. And they kind of like this cycle that they live in, where you edit your code, you compile the code, you run the code fails, you figure out why, you edit it, and you just kind of repeat. There's a theoretical edge that goes from run to succeed, but I don't think most software projects ever take that. We just live in this loop forever. And every time you get a compiler rejection, it's preventing you from going in this loop, which is interesting. You go edit, compile, and instead of being able to run it and see the bug, the compiler tells you that there's a bug there and just forces you to edit again. And so a lot of these cycles that we're not getting to participate in, we're still learning something. We're still having this dialogue with the compiler, and we're avoiding having to do the diagnosis after the failure when we run it. And so the fact that you're fighting the compiler shouldn't really be viewed as a unfair process where the compiler is not letting you run your code. You should view it as it's preventing you from seeing things at runtime, and it's also making it so things that may be extremely difficult to diagnose are just being told to you, like, here, this weird memory thing is going on in your code. I'll stop you from even compiling it so you can fix it now. So why should we care? So there is this pressure from above. There have been a number of these. This is the most recent one, where basically they're saying we need to take memory safe languages seriously, and companies and large projects need to have a roadmap for how we adopt these. What's interesting about this one in particular is that they're not aiming it at developers. So they're saying C-suite executives, technical experts, so decision makers, they need to think about it. Essentially, they're kind of telling them, you need to take your developers' advice seriously and invest in these. The other thing I thought was interesting about this one is it's not just the usual suspects like CISA. This is essentially all the Five Eyes saying, you developers, executives, you guys need to take these things seriously because we're kind of tired of trying to protect you from yourselves. So this, I think, is pretty important. And this means that we're going to probably get pressure from above. We do have direct safety and security concerns. So we build systems for high assurance applications where we have very high security and safety requirements. And as part of that, we need to make strong and defensible arguments that our software meets those needs. And that's where the memory safe languages help you, is they help you with that strength and defensible argument that your code is actually correct. And I'd say that our current practices to assess correctness are somewhat limited. Testing, it's better than nothing. Like, it's good that we do testing more than we used to. But the problem with testing is you can't extrapolate to cases you haven't tested. Certification activities that are kind of like, you've got some forms and you go through a process, you have a meeting, you have people kind of walking through a formalized process, and you check things off in Excel spreadsheets. That helps you because you've actually looked at the code and had more people look at it. But again, this can feel more like a paper pushing exercise than an actual assurance exercise. And static analyzers, when we try and apply those, my observation in building them and giving them to people is that they often tune them out because they get drowned in false positives. And sometimes they even miss things. And so memory safe languages are a tool to give people kind of a stronger assurance case about the code that they write. But not all of us are building high security and high safety requirement things. So why should we care about those? So I've heard people say, I don't write internet facing code. It's not network code. It doesn't apply to me. The problem is you don't want to be the person who's provided the attack surface for somebody else. So every component in the system is something that an adversary or a bug may use to kind of do something unexpected. And this complicated attack that was publicized in the last month or two that was on iOS devices, it ended up going through huge numbers of software components. And I really doubt that the people who put this instruction in the TrueType font library in the 90s anticipated that they would be a critical component of a network-based attack later on. So there was a software defect. I don't think it was a memory safety thing, but it was a software defect that was in a non-network facing software that allowed people to build a network-based attack. And so even if you're not writing what you consider to be performance or safety critical or security critical code, you are code and you're providing something that somebody else could use if you have defects. So you don't want to be the one who provides the attack surface. So if we're considering how to apply these at the lab, kind of the biggest considerations are cost, obviously, time and effort costs money. There's human factors, and we also have to figure out when and where to apply these things. So I have a few thoughts on these areas. So cost, this is not going to be free. We all know that. You need to be able to pay not only for the time writing the code, but the professional development to make it so people become proficient in working with these sorts of languages. And to be honest, even though I'm talking about memory safe languages, professional development, I say, would also include training people up on, say, modern versions of C++, so that somebody who's only up to C++ 11 in their background becomes familiar with C++ 17, C++ 20, all the new features that have been added that help you write sort of safe code in C++. That also qualifies in this area. The other thing is funding agencies typically are very difficult to get to kind of pay for things. So software maintenance, technical debt cleanup, modernization has been very hard to get funding agencies to pay for. My hope is that this pressure from above, well, that pressure is above our funding agencies as well. That may motivate them to be a little bit more open to funding software maintenance and software quality work that they wouldn't have traditionally funded. But either way, this is going to be expensive. The people factors, though, so the support one here is basically, I think if you are on a team or you're kind of participating in a project and people want to push the boundaries on possibly writing safer code, I think they should be encouraged to do so. I wouldn't discourage somebody simply because, like, oh, well, we don't do that language or we're not interested. I think it's useful to allow people to push the boundaries. But on the flip side, language people can be a bit zealous. They can be a bit like a little crazy when they get really into a language. And there will be people who are kind of working with the traditional tools who have very valid concerns about, oh, I don't think it's appropriate to use this memory safe language. And so I think it's useful to be able to listen to those people as well, because we don't want the memory safe language zealots to kind of just bulldoze over them, because there may be unintended consequences of that. The other thing is people tend to really love their tools, like really love their tools. We see this a lot in like the editor wars. And this love for the tools can often breed pretty negative responses. And I think the way people should treat this when you have somebody who's like a C++ developer who gets very defensive about what they think they can do with C++, I don't think that that's really, we need to treat this as something where it's like basically a big shift in technology like this that we're asking for is asking people to give up basically a lot of hard-earned investment that they made in learning these things. And so you got to recognize that's a valid concern. This isn't just like a religious response. This is somebody saying, I've spent 20 years being good at this. I don't want to give it up. The other thing that's going to happen, though, is the cycle of life will happen. We're all going to go away. And what I've observed with new graduates coming out of school is that if they've learned more than Python, they often are interestingly positive on memory safe languages. A lot of them know them or are familiar with them and want to work with them, and they'll eventually replace the existing workforce. So I think the shift to memory safe languages is probably going to happen naturally, just because of the cycle of life. But I don't know if we have time to wait for that natural replacement to occur. Another thing is we need to be careful about where we apply it. So usually when people hear memory safe languages, they hear Rust, and I think that's a mistake because I don't think it's the most appropriate language for every context. And this is happening a lot where super eager Rust people are running around trying to apply it to everything. It's not the best for every language. I mean, myself, I build compilers and static analysis tools, and there are times when the Rust language, when I've tried it out, has gotten in my way. And I can achieve the same level of safety. So I can write it in a memory safe way with nice guarantees in another language like OCaml, but I can express it in such a simpler way. And so sometimes these languages do have friction if you try and apply them inappropriately. So I think the fact that there are lots of options is good. We can pick the appropriate tool for the appropriate job. On the other hand, lots of languages can lead to this Tower of Babel problem where we end up having this kind of chaos of different projects are choosing different languages, and now nobody speaks the same language. You can't work on different projects, and you can't have interoperability. And so it could be a bit of a mess. So I don't have a good answer to this. My only recommendation here is be more open than just Rust. If you're interested in adopting memory safe languages into a project, don't just default to Rust. Look around first and see what options are out there. So if I had to match up domains that we do to languages, I mean, we do some embedded spit work. And if you look at things like you're using VxWorks, well, that ships with Ada. Now it ships with Rust. And so you can do more than C and C++. And outside VxWorks, Rust is appearing in other embedded contexts as well. If you're building developer tools, you don't need extreme performance, but you generally need more than Python gives you. And so kind of the compiled languages like Swift, Rust, OCaml, those are strong contenders. I didn't mention it before, but some of the JavaScript derivatives that kind of try and make JavaScript a little bit less horrible, like TypeScript and Reason, these are very good for building user interfaces. So if you have to build an interface that somebody's going to be sitting at, and you want to make sure the interface doesn't have problems, you can appeal to those, or the enterprise style languages. Server tools, Rust, Go, C#, Java. But the big gap is HPC. If you look around, there's not a lot of tooling in these languages that supports high performance computing applications. And this is where I think we can flip it around. And as one of the places that really pushes the HPC community, the fact that there's a gap doesn't mean we should reject the languages. I think we should see that as kind of a opportunity. It's a place to get citations. It's a place to build things that help push the technology forward. And I think we can help in that front. So when do we do this? So like I said, HPC, I don't think it's ready yet. And so we don't really want to just jump straight in and expect it to work. But the timing really has to account for how critical the system is. So if you're dealing with embedded or instrumentation or networking or cybersecurity tools, yeah, you want to do it sooner than later. You're on the forefront where you have those direct security and safety concerns. But the data crunching, modeling, and simulation, in those cases, you're more likely to be providing the attack surface for somebody else, or you may have a bug that's not that critical. So you want to eventually do it, but it's less critical. The timing, though, should not just be the plans to adopt the technology, but the precursor steps to mature it to the point of being ready. So like in the HPC space, you can't really time when you're going to do it now because it's not ready. You have to actually be playing the game of what is the timing for the precursor steps so we can plan for it. And this is where we should participate in the process. And I'm going to tell two stories here that are related to this. And this is kind of near the end of the talk. The first one's a sad story where people failed miserably to do the precursor steps. And the other one's a happy story where everything came out good. So the sad story is, so this is the beginning of my career. So like I said, I started my career at Los Alamos, and I remember being in the meetings that took place in the couple of years before this happened. And Doug Post had a couple articles in this presentation, kind of doing a retrospective 20 years ago on the ASCII program. This is the ASC program turned into this one for whatever reason they dropped the I. So there were some interesting lessons learned from this because it didn't go as well as people had hoped when they initiated it in the mid 90s, because the whole premise of the program is to modernize the codes that we use for the stockpile stewardship program. And buried in his presentation is something that I remember very clearly happening, which was some of these projects made the mistake of needing to employ modern computer science techniques. They were pushing the limits of computer science, but the computer science research hadn't been done yet. Interestingly, the stuff that caused some of these projects to fail most was C++ template metaprogramming. In the 90s, the concept had been introduced, but compilers were way behind the curve. And so people didn't know how to compile them efficiently. They didn't know how to do some of the things they wanted to do in the template metaprogramming system to do it correctly. But they adopted it anyway and started saying, we're going to build a new full 3D code in just a few years using all this fancy new computer science research. And that project augured itself into the ground horribly. I remember being in the meeting where they said, here's the 4 code projects at LLNL. These 2 are canceled. And there was a lot of sadness, but it was kind of unavoidable because they spent most of their money, at least half the money, on the computer science research, even though they were supposed to be spending the money on physics and building the 3D model or the 3D modeling and simulation code. And this was a huge failure. I mean, 100 million bucks. This was bad. And this left a really bad taste in people's mouth for things like template metaprogramming and C++ that really took a while to heal from. But what's interesting is the fact that they did it early wasn't in an indictment of the technique that they wanted to use. It was just they planned it poorly. And if you look now at things like Raja and other toolkits that are out there, they're actually using this technology and they're successful. But that's because the technology was ready now. And so these precursor steps to adopting a language are very important to plan for. You have to be realistic about how you, well, hey, LLNL hasn't healed. I don't work there anymore. There's good reason for that. So that's a sad story. Or at least it was sad being in the audience at LLNL when they canceled the code projects. But the happy story. So the year is 1996. This is when I first got into scientific computing. And at the time, people wanted scripting languages. Like there were a number available. You had Tcl, you had Perl, you had Python. Ruby existed, but the documentation was mostly not in English yet, so it didn't really get a lot of foothold. And there was still competition. Like the bioinformatics people were running around doing Perl. Tcl, I don't know who was using that. And Python was out there. I think the particle physics people actually were Tcl users for some reason. And then a handful of enterprising people said, well, we want to use Python, but it doesn't do numerics. Like it's terrible performance-wise. It's missing a lot of things. And so some people built numeric and numarray, and somebody wrote the Swig wrapper generator that let you take existing code and wrap it up and make it accessible through Python. And what was cool about this is all of a sudden, 20, 30 years later, we have NumPy, which powers basically most of scientific computing outside of HPC, machine learning, data science. Like Python is everywhere. And the thing that makes me happy about this is if you look at these precursor things like numeric, Swig, numarray, and you look at the authors, where'd they come from? The national labs were the ones who pushed the limits. Livermore was participating in the numeric or numarray, one of those. Los Alamos participated in the Swig. And so the national labs recognized this gap. They recognized the need, and they put in that time to get the technology up to the point where it was useful. And all of a sudden, now it's the bedrock for a whole chunk of the scientific and now industry with machine learning community. And so I think it's kind of a good thing, and this should be a way of thinking, maybe we can do this again for memory safe languages. So the last slide before people can chat a little bit. So memory safety, I think it's a good thing. And even beyond memory safety, any form of language enforceable safety should be considered a good thing. And there's pressure mounting to take advantage of it. So we might as well. The opt-in model of safety, honestly, it hasn't panned out. 40 years is a long time to be like waiting for this to kind of work. And I don't think it's going to all of a sudden just because Strustrup gave a talk last year saying that static analyzers will help. I mean, they haven't helped for 40 years, and I doubt they're going to all of a sudden help. So opt-out appears to be more trustworthy and more predictable. Even though Rust is the most famous of these, there's many options that fit the bill. I think a slow migration is the right thing to do. Don't jump right in. Don't do what the Puma team did at LLNL and just say we're going to dive right in and apply one of these immature technologies to a production code. That would be a mistake. Interim use of these safer features for existing languages is a good thing, but for the long term might not be ideal. And when you see these gaps, especially in things like HPC, don't just reject the languages outright. That's actually an opportunity. We might as well. It'd be great if one of us was the person who gets cited a bunch for laying the foundation for doing HPC in a language like Rust or Swift or something else like that. So that's it. I'm a couple minutes behind when I wanted to be, thanks to my little technical glitch. But I figured I've seen the little bubbles, but haven't been able to read them very much about the chat. But I'm happy to answer questions or hear thoughts or opinions or anything like that.
Yeah, thank you, Matt. Really great talk. About 10 minutes in already, people were requesting to get those slides released and make this recording available.
Sure. Yeah, I mean, I'll put the slides into IM, and then should I just send them to you?
Yeah, that's great.
Okay.
So we did have a couple or pretty good discussion in the Slack already. So I think one thing that was mentioned is what's the best option for the HPC world right now, and the data science realm as well, I think.
So I did think about this a little bit with like if I had to go to an HPC code team and say like, okay, where should you start thinking about safety? There's two components. So there's some parts of the infrastructure I think are appropriate to start thinking about migrating sooner than later. So things like IO layers, like if you were to look at like HDF5 or some of these things where they're not the compute heavy things, they're doing more infrastructure related things. Those are more systems like pieces of code, and some of these languages are close to being ready for that. It's the places like the actual numerical core or the message passing or some of the parallelism. Honestly, like you can find MPI bindings for some of these, but they're very immature. And so that's a place where it might be more worthwhile to migrate like the existing C++ to using newer C++ features, like maybe adopting move semantics, maybe doing something where you're trying to impose a pointer discipline on everything through either using the STD various pointers or using some libraries or doing things like LLVM did where they build some helper objects to give you the safety. So that's kind of where in the HPC world I would do it. Data science, I mean, you got Python, which is already providing some safety guarantees. I don't really know. I mean, there are some other languages that are kind of competing with Python, but I don't know. They're very immature, like Julia. Latiner apparently has this Mojo thing coming along, but I have no idea what that is. It seems to be, maybe it's released. I don't know. But there's also moving Python to adopt some of the more recent PEPs. So like PEP 484, I think was the type annotation one. And so the Python communities recognize there's places they can make the language safer, and they've been adding some of these things into the language. And now you can like use type annotations and then run a linter or a static analysis tool on Python and see problems that you normally wouldn't have seen before. So that's kind of what I would recommend in that world.
Yeah, thanks. Yeah, I think Julia would be a good one to mention. I think that's making some inroads in the HPC space at least.
Yeah, I mean, Julia is a cool language. The thing about Julia is that in some experiments I did with it, it's just the performance can be a little bit hard to predict. Certain algorithms, the compiler just doesn't do a good job on. So,
right. And I also think one of the limitations with HPC right now is that we're basically in the hand of the GPU vendors. So,
oh yeah, I forgot about that. Yeah, that's another thing that's completely missing is not all these languages help you with GPUs. So that's a huge gap.
Okay, any other questions?
Do we do much 830 code development with memory safe languages?
Say that again?
Well, I think I'm using the right nomenclature. These 830 codes that we develop, these are like extreme safety codes. They have a higher software quality assurance requirement. Do we do those with memory safe languages? Do we know of? And if so, do we even measure how much we reduced memory bugs when we did that?
I have not actually seen a memory safe language used here for any critical system. Now, I do not have insight into a huge number of projects here, so I'm not going to say we don't do it, but I haven't seen any myself. I've seen a lot of C and C++, and usually there's a lot of heavy use of things like static analyzers, where we'll take a C code and then basically throw every static analyzer that we can get access to at it. And then they do raise bugs, so we do find bugs that way. But that's the best I've seen. And I've talked to people across the street at Sandia where they do a lot more embedded systems work and a lot more things where they're kind of in this world of very critical systems. And they have expressed the desire to move to these, but they still do a large amount of C development. They've used a different style, though. They use what's called a certified compiler so that they can prove properties about the C code. And that allows them to get safety. So.
Okay, thank you.
Okay, any other questions?
So is there any initiative or talk about moving more to memory safe languages at the lab here?
So the reason I gave this is because there's been kind of buzz amongst kind of management types who may initiate initiatives or try and impose rules. There hasn't been like any official like push. But I think people are kind of asking the technical experts to inform them. So if somebody's going to say, oh, we're going to make a push in LC or in some part of comp or SD to do some of this stuff, I think they're kind of waiting on the technical experts to kind of tell them. So hopefully we can maybe as developers tell people above us that, hey, we should have an initiative to take some component that we know is critical and start saying like, maybe we should start migrating, or if we're doing a brand new project, making sure to say, hey, let's use this as an opportunity to build this one in a different way from the start. But I don't think there are any official initiatives. And to be honest, I've kind of pushed back a little bit when people have asked like, hey, should we have one? I'm like, no, the last thing we need is managers telling us to do this, because they're gonna miscalculate the time, effort, difficulty, and appropriateness. So I think it should be developer informed, not manager informed. Hopefully there are no managers on the call.
Okay, thank you.
Yeah, and if people think of anything else and want to email me, feel free. So Satili2 at the lab. So, and I'll share the slides.
Okay, great.
Thanks, Matt. This was great.
Cool. Well, thanks for coming.
Yeah, absolutely. So thank you, Matt. Really great talk. And yeah, let's applaud our speaker.
Cool. Thank you.